In the previous video, we looked at how to solve trigonometric equations. In this video, we'll look at some more complex trig equations that require us to do a bit more algebraic manipulation before we can solve them. Specifically, we'll look at quadratic trig equations and trig equations with multiple functions. Let's start with quadratic trig equations. We're asked to solve for x and given 2 cos squared x plus cos x minus 1 is equal to 0, where 0 is less than or equal to x is less than or equal to 2 pi. So that tells us that we're working in radians. Now first let's think about what this is asking us. It's asking us to find the angles, x, that when we put them as input into our function are going to give us a true statement. In other words, when we evaluate the left-hand side, we'll get 0 as we get on the right-hand side. Now, the first thing to recognize here is that we've got several instances of cosine, so we're not going to be able to solve this equation as simply as we did in the last video. But notice that we can rewrite it like this. That cos squared x means take the cosine of x first, square it, and then multiply it by 2. If we write it out this way, we can see that repeated cosine x is itself the variable of a quadratic function. If that's hard to see, let's let cos x be equal to, and we'll introduce a new variable a. If we do that, then this becomes 2a squared plus a minus 1 is equal to 0. And now it looks like a very familiar quadratic equation. We can factor that and get 2a minus 1 times a plus 1 is equal to 0. Remember, we're using a as a stand-in for cosine of x. Now, if the left-hand side is equal to the right-hand side, then one of these must be equal to 0. Either we've got 2a minus 1 equals 0, which solving for that we get a is equal to a half, or we've got a plus 1 must be equal to 0. In other words, a is equal to negative 1. Now we've simplified and solved the quadratic equation here, but we've done it in a, and our original variable was cosine x, and ultimately we want to find what x is. So let's replace a with cosine x. We get cosine x is equal to a half on this side, or over here we get cosine x is equal to negative 1. That means that x is equal to either the inverse cosine of a half, or x is equal to the inverse cosine of negative 1. And in both cases, we're on this domain. Now, if we think about the related acute angle that has a cosine of a half, that's going to be pi over 3. And if we put that in the quadrants where cosine is positive on the right-hand side of the Cartesian plane in quadrants 1 and 4. So that would be pi over 3 here and pi over 3 here. That means that the principal angle is pi over 3, or this one would be going all the way around to 2 pi and then coming back pi over 3. So 6 pi over 3 minus pi over 3 is 5 pi over 3. So the solution to this branch is x is equal to pi over 3 or 5 pi over 3. On this side, it might be easiest to think of the cosine graph, which looks like that. We're asking what's the x value that corresponds to a y value of negative 1. In other words, what's the x value here? And that's 180 degrees if we're working in degrees, or in radians, it's going to be pi. Alternatively, you could think of the unit circle and ask, what is the angle that has an x value of negative 1? Remember, cosine is the x value on the unit circle, and again, that's going to be 180 degrees, or pi. So the answer to this part is x is equal to pi. Therefore, the solution to the whole thing is that x is equal to pi over 3. I'll put pi next so that I'm going in increasing order, or 5 pi over 3. Plugging any of these values into the original quadratic equation will give us a true statement. We'll get 0 on the left side and 0 on the right-hand side. So the approach that we used was here to write it this way so that we could see that it was a quadratic equation. We replaced cosine x with another convenient variable a, solved the quadratic equation by factoring, replaced a with cosine x again, and then solved. The next type of more complex trig equation that we'll look at are trig equations with multiple functions. And here the key is to use identities to put the whole thing in terms of one function. As an example, we could be given sine x is equal to root 3 cosine x, where x is once again between 0 and 2 pi inclusive. So once again, we're working in radians. Now what makes this a little trickier than simply something like sine x is equal to a half, for example, is that we've got this extra cosine x. And adding or subtracting sine x or cosine x to either side will still leave us with the two functions. So the thing to try is to divide. And if we divide both sides by cosine x, we get sine x over cosine x is equal to root 3. And this, remember, is the definition, or one of the definitions, for the tangent function. So the left side simplifies to tan x is equal to root 3. This you'll recognize as one of the ratios from the special triangles. So x is equal to the inverse tan of root 3, and because it's from the special triangles, we can do that without a calculator. You'll recall that the angle that has a tangent ratio of root 3 is pi over 3. So we know that our related acute angle is pi over 3, and we need to ask ourselves which quadrant that goes in to have a positive tangent ratio, because the tangent ratio is positive. Well, it can go in the first quadrant, or it can go in the third quadrant. That means that the principal angle is either pi over 3 in the first quadrant, or going around to pi, which is 3 pi over 3, and then another pi over 3 gives us 4 pi over 3. So x is equal to pi over 3 or 4 pi over 3. Again, the process here was we divided both sides by cosine x. That simplified the left-hand side to tan x, and then it was clear that it was from the special triangles. Now, one thing that you should notice here is that we're dividing by cosine x. And remember that the one thing you can't divide by is 0. So we have to be sure that cosine x is not equal to 0. Well, if you look back at the original equation, if cosine x is equal to 0, then the whole right-hand side of the equation is equal to 0. And the only way that this could be a true statement, that this equation could be true, would be if the left-hand side was equal to 0 as well. But notice that cosine x, which looks like that in its untransformed version, where that is 2 pi, and sine x, which looks like that in its untransformed version, roughly, are never 0 at the same place. They never have the same x-intercepts. Sine x has x-intercepts at 0, pi, and 2 pi, and cos x has x-intercepts at pi over 2 and 3 pi over 2. So if the right-hand side is 0, that means that we're here or here, then the left-hand side can't be equal to 0 because sine x doesn't have an x-intercept there. In other words, we don't have to worry about cosine x being equal to 0 because that means that the original statement couldn't have been true in the first place. Therefore, we can divide by it because it's not equal to 0. Let's look at one more example that combines features of the previous two that we looked at. We're asked to solve for x, where 3 tan x minus 2 cos x equals 0, and x is once again between 0 and 2 pi radians inclusive. Now, because we know we want to get everything in terms of a single function, let's rewrite the tangent x as sine x over cosine x. And then we have minus 2 cos x, as in the original equation, equals 0. This is at least a step closer because here we have the possibility of turning the tan x into something resembling cosine of x. We didn't really have the potential for the reverse. Now, we want to get rid of this fraction, and the way to do that is to multiply by cosine of x. If we were to multiply this by cosine of x, it would cancel out with the denominator. We can only do that if we multiply the whole left side by cosine of x and the whole right side. If we do that, then the right side becomes 3 sine x, because the cos x's cancel out, minus 2 cosine squared of x, because I've multiplied cosine of x by cosine of x, and the right-hand side is 0 times cos x, which remains 0. Now, we're even closer to getting the whole left side in terms of a single function, because recall that by the Pythagorean identity, sine squared x plus cosine squared x is equal to 1. And therefore, cosine squared x can be written as 1 minus sine squared x by moving this sine squared x onto the other side. So we get 3 sine x minus 2, and replacing the cosine squared x with 1 minus sine squared x, we get that equals 0. Now, if we distribute the negative 2 in, we get 3 sine x minus 2 plus 2 sine squared x is equal to 0. Reordering that in the way that we're used to seeing quadratics in decreasing powers by each term, we get 2 sine squared x plus 3 sine x minus 2 is equal to 0. And that can be factored as 2 sine x minus 1 times sine x plus 2 equals 0. And if that's hard to see, remember this is the step where in the previous problem we would have let sine x be equal to a, and then this would have become 2a squared plus 3a minus 2 is equal to 0. And then we factored and later would have replaced a back with sine x as in the first example. But if you can see it, you can go straight to here. That means that we've got either of two things happening on the left side for it to equal 0. Either 2 sine x minus 1 is equal to 0, or sine x plus 2 is equal to 0. Solving each of these in turn, we get sine x is equal to a half, or x is equal to sine inverse of a half. Solving this one, we would get the related acute angle that has a sine ratio of a half is pi over 6. And to have a positive sine ratio, we've got to be in the top half of the Cartesian plane, either in quadrant 1 or in quadrant 2. Therefore, the principal angle, the angle from the positive x-axis, is either pi over 6 or pi minus pi over 6, which would be 5 pi over 6. So this left branch of the equation gives us x is equal to pi over 6 or 5 pi over 6. Now we go to the right branch of the equation. Moving the 2 to the other side gives us a negative 2. We get sine x is equal to negative 2. Now if you think about what this is asking, thinking about it graphically means you're looking for the intersection of y is equal to sine x and y is equal to negative 2. Those don't intersect because the minimum value of the sine x function is negative 1. Another way of thinking about it, remember sine x is the y value on the unit circle. It's asking what's the angle that corresponds to a y value of negative 2 on the unit circle. And there is none because the unit circle is only 1 unit in radius. So this has no solution. And that will happen from time to time in these kinds of equations. If this has no solution, we don't get any solutions to the original equation from this branch. We only get these two. So our final answer then is x is equal to pi over 6 or x is equal to 5 pi over 6. And plugging either of those back into the original equation will give you 0 on the left side, which equals the 0 on the right-hand side. So those are some examples of more complicated trig equations.